So I got this 15-bit RAM stick for the 16-bit computer that we're building. It has a lot of pins on it. So instead of trying to plug it in and mess around with it through hardware, I'm going to test it out through software first. Something like this, an Arduino Nano. The only problem here is we have 15 bits of address and we have 8 bits of data. So that's 23 bits total that I need just for the data transfer. There's also a read pin, a write pin, and a chip select pin. Altogether, it seems to be about 26 pins that we'll need from our Nano, and I don't think we have it. Some of the analog pins that we can use as well, but it's still not enough. So I think what we'll have to do is use one of these guys, a 74LS164. This is a shift register. So what we'll be able to do is essentially get more pins out of the Arduino by using this register. We'll be able to bit bang data onto these registers, sort of using them as expansion slots. So why don't we test it out first? Let's see if we can get 8 bits onto the shift register to create 8 new pins for our Arduino. Let's try and get that going. So let's start plugging everybody in. And so the way this works is we bit bang on these 2 pins here. These 2 are going to be joined together. And whatever data is in here, when we hit the clock, it will jump to A's output. And then when we hit the clock again, whatever is in A will go to B, whatever was in B will go to C, and it'll just pass it all the way down. So if we had 101 and we hit the clock, then it'd be 101. And if we hit the clock again, it'd be 101, and it will just continue passing it. We can save as much as 8 bits here. VCC up here, the 2 inputs need to be tied together. Let's do that. So when clear is low, it will just keep everything at 0. So we're going to turn that on. We're going to pull it high so that it's not continually clearing all of our data. We need to bring down the ground over here. And now we need to, I guess, power up the actual power rail with our Arduino. All right, pulling the ground in, and the 5 volt is where he's right here. So I'm going to bring him here and then transfer him across after. And then I'll bring him across. That's most of the connections, I think. Now what we just need to do is make sure that we can see our outputs, which is the whole point of this. We can test this out. So I'm going to put resistors across into LEDs. All right, there's our first 4. Or the next 4. So now we just need to bring the LEDs down here. So I guess I'll try and connect them into this row here. All right, here are 8. So now what we need to do is choose a pin that we're going to use as the output, and I'm just going to use maybe 4. I like to save 2 and 3 for interrupts. So I'm going to use digital 4, and it will just go into one of those inputs since they're tied together on the green, and then we need the clock. So the clock is going to be, I guess, digital 5. Edge over here. All right, I know it's really hard to see. I apologize. So let's plug in the Arduino and write some code and see if this baby works. Shift data pin is at 4, and we know that shift clock is at 5. I think that's where we put it. So to get it started, let's just use a simple function, and then we can perhaps optimize up to that if it's running too slowly. So we're going to say that we want to output on those 2 pins, hammer out some bits, and see if we see them going out on the shift register. So let's just make a simple integer, increment it until it's around 8, and let's just toggle vals. And then all we have to do is toggle the clock. So digital write, shift clock, pull it high, and then pull it back low. And this should work. So let's just run this and see what happens. Okay, wow, that happened really fast. I think there's one missing here on the end. I'm not really sure. It happened too fast for me to see, so I'm going to add a delay here. It's 500 milliseconds. Moving now. So the last 2 lights seem to have an issue. I guess these resistors are not in properly. All right, so it's alternating. That looks like a good sign. I guess we should plug in the clear real quick. So this gray guy, digital 6, clear. So now let's modify our code real quick. And so they shift clear 6 and output. Every time we start, we'll just clear. And I guess we could even just put definition up here just to make it easy. Let's test it out by clearing it after we do everything. So let's do like a delay of like 2 seconds and we'll clear. So now we should see every other bit fill up and then it should clear after 2 seconds. All right, we seem to have some activity there. They're moving themselves along, and then we should have a clear. Nice. The lights looks a little weird, but I'm guessing it's more my connection. Now what we can try and do is write some data to it. So let's make a function shift W for shift right, and we have 8 bits, so let's do an 8-bit value. And what we need to do is iterate through the bits. So we're going to write to shift data the value of val and 1 bit shifted to the left of i's value. And then we'll just check if that's greater than 0. And that should work. And then we have to toggle our clock. And after that, we'll just delay so it's not super immediate, like 500 milliseconds each. At the top here, we don't need any of this anymore. We just need to clear it. And then we can call shift W and put the value like 5. All right, there's our data. And it looks like we are going to end up with 101. Let's write some other messages here. And between each call, let's just delay like 3000 so we can look at it. And then let's write some other values here. 7, it's 111. Actually, instead of making all these delays, I'll just add it to the function. So let's write the letter A. So we're expecting to see 101 on the least significant bits, 111, and A should be like 01 with a bunch of zeros and then 1. Let's see what happens. So it should clear off the bat, which is really cool. And then we should see 5 come back out that we had, 101, perfect. 3 seconds later, the next one starts coming out. And it looks like we do have 111, which is 7, great. Now we have A, which should be a bunch of zeros in between, and that looks like A to me, 0, 1, 0, 0, 0, 0, 0, 1, 64 plus 1, 65. Awesome. So I'm going to remove the delays now because the chip can actually go faster than the Arduino. See if it flashes on. All right, there's 101. There's 111. It's instantaneous to my eyes. There's the A. So crazy how fast machines work. So the idea here is that we can pump out the address here, right? And we're only using, if you want to call it 3 pins because we have to use it clear, but really it's 2 pins to get this data out. So our 2 pins from the Arduino are turning into 8 on the shift registers that we can then use for the address. And of course, we're going to have 2 shift registers to reach 15 bits. So imagine another one of this, and we'll have 15 bits of address space that we're able to get from 2 pins on the Arduino. So really sort of multiplying our force. That leaves us with enough pins on the Arduino to get the raw RAM input. So from here, I guess I should try and connect the RAM together, connect the other chip, and see if we can get some testing going. We need to look at the datasheet for this because I don't know exactly where how the pins are laid out. I'm going to try and get this plugged in, get the other chip plugged in, and put everything together. All right, so let's start by connecting the lower byte of the address. All right, here's our first byte. So we can say that's the first byte of our address, the lower 8 bits. And now let's move on to the second 8. So the plan here is we're going to shift everything onto the shift registers from the microcontroller. So we're going to bit bang them on, and it's all going to load the address, basically buffer it for us. And then we're going to be connecting the lines that go from the shift register to the RAM itself. So the RAM, when we trigger it, can pull the address from the buffered address that we have on the shift register, and then it can either send the output to our microcontroller or read the input from our microcontroller. So now that we have the first half of our byte done, let's do the second half. But now you can see that 0 through 7 were pretty straightforward, but now it just jumps around everywhere. There's 8, 9 on the right, and then 10, 11, and it goes up and down and backwards, and I don't really get it, but let us just continue. And now we're going to be on the second shift register, or the first one I should say. And then so that's 8, 9 is directly below, that's convenient. 10 is in a weird spot. Next bit from the shift register, like that. 11 is next to 9. 12 is now where we were before on this side over here. And then 13 is next to 8, which is our yellow right here, so the one next to it. And then 14 is on the end here. So here's our address. I guess we can call it a bus. Pretty fluffy here. The input output are just here. We can see on the schematic. So I'm going to connect them to the microcontroller and then connect all the power and everything together. All right, here's him complete, hopefully. We saw the addresses going in, and you can see now that the shift registers are jumped together. I didn't want to have LED indicators for every single bit of the shift register, so I just used one resistor here on the first bit that's ever shifted onto the shift registers. I'm outputting that to an LED here just so that we have like an indicator. If you think about like a hard drive light or something, we could just see that there's activity going on as it starts to hammer stuff out. So we'll see this blinking hopefully as we put data on the, what I'll call the bus, the address bus, I guess I'll call it that. This bottom pin here, the bottom left on the schematic, bottom right component is the ground. We have the IO pin. They're going into on this kind of like Rainbow Road looking Super Mario Kart Rainbow Road level. Beautiful bus right here. It looks really nice. I was able to keep those together. From this point to this point, this is our data bus. I guess the most important things are the control lines. I tried to offset them so that they're pretty obvious. So this white one here, you can see it's offset from the rest. That is the write enable pin. So we can write with the white one and we can bring data back from the RAM with the black one. The black one, you can see it's also offset. It's coming out a bit. Yellow one that's also offset is the chip select. Basically activate the RAM. And then this line here is a clock for the shift register. So all on this side is pretty much control lines. Red cable here is going into the first shift register to be able to hammer out the bits onto it. And I think that's pretty much it. The clear is again pulled up by the VCC. I no longer need it connected to the Arduino, I don't think, because every time we shift out, it's going to automatically clear since we're always going to be shifting 16 bits. Even though the RAM only takes 15, I'm going to be shifting 16. So time to plug this in and let's adjust our program, or maybe write it from scratch. I don't know which one is better. I'm going to put this at an angle. Hopefully we can see this light going off as we begin to test, and we can see that the power is on. I think I'll just start fresh here. We didn't really do much, and it'd be good reinforcement to do it again. So what I'm going to do first is just set up all the definitions. So we have our little control center pins where we have the write enable, output enable, chip select. And the values for these, I think, are 15, 16, and 17. Next, we have the shift register. So we have shift data and we have shift clock. Data is on pin 13, shift clock is on 14, which is the same as saying analog 0. And then we're going to need our actual data bus pins. We could do each one like data 4, data 1 could be on 5, and we're going to have 8 of them. But I'm just thinking we can have the data start could be 4, and then we just have the data length, which will be 8. So we can start at 4 every time we need to enumerate through the data pin, loop 8 times, gather all the data. So I'll do it that way. And then instead of doing the shifting as manually before, I think I'm going to do definition here. We know that to shift, we have to do 3 things, right? We have to set the data, then we have to pull the shift clock high. This on itself, these 2 steps will make it pulse, but then we'll reset the clock low, put it back to idle pretty much to use it next time. So we're going to do digital write, and we'll do shift data, and we're going to put in X. Then we're going to pulse a clock high for going back to low. And then I'll add a little delay here, like what we had last time, maybe half a second. And then I guess we can test it out and just make sure that we have blinking on our light. So I'm gonna go into the setup here. We need to set all these pins to output. Write enable is gonna be output. Output enables output. Chip select output. Shift data output. Clock output. These pins are gonna be set whether we're writing or reading from the RAM. So I won't do that here. We're gonna use a serial here, communication from our computer, so we can see what's happening. So I'll just do 9600 bits per second. Print it to the screen. Run this and make sure that it works. All right, there's our message, so everything looks good. So now what we should do is add our shift function, and we're going to pass in a 16-bit address, right? And we're going to need to put that on the shift register like what we did with our first test, but this time it's 16 since we have the 2 shift registers together. We just loop through them in the same way. I'm going to do it dynamic so that in case we send a different value, we don't need to change the code. So size of address times 8, because the size of address will be 2, right? 2 bytes, so times 8 is 16 bits since we're working with the bits. So we're going to shift using our definition. And we're going to take the address and have an evaluation here. So if address and 1 bit shifted I amount to the left is greater than 0, then it will send a 1. And if it's not greater than 0, then it will send a 0. And I think that should work. I guess we should test this out. Function prototype up here in the setup call shift, I guess. It needs to be 2 bytes. That's 4 hexadecimal digits. So let's do 5s because that toggles 10101010. So let's see if this works. All right, and there is 1010101010. 101010. So that seemed to work okay. All right, so now that we can put stuff on the address line, all we have to do is set up our RAM module. So the way it works is we need to actually set these to be high first. So we're going to do digital write, just basically putting them all into an idle state. So they're going to all be high. And then now we need to work on our actual function. So we'll just do void, and we'll do memw for memory write. And to write, we're going to need an address. So we'll have the same 16-bit address, and we'll have an 8-bit value. What do we need to do first? We're going to shift, of course, the address. So we're going to call shift on the address itself. That's the first thing. And then so we also need to put our data on our output pins. The same pins that we're using for input-output. So we need to make sure that they're outputting and not inputting. So we need to basically loop through it. And I is 0, I is less than data len, which is 8, I plus plus. And what we're going to do is we're going to start on data start, which is pin 4, but that doesn't matter, plus I, right? And then we're going to set it to output, right? We're writing, yeah, output. So it's going to start with 4 plus 0, which is 4, the first one, then 4 plus 1 is 5, and 4 plus 2 is 6. So hopefully this should hit all of our pins that are carrying the data. Basically, let's call it our data bus, setting them up for output. And then I guess within here, we can actually write to each one. So we'll do digital write, the same thing, data start plus I, so the same pin. And then now what we need to do is get the value from the bit that we're on. So we're going to put val, because that's the value that we're sending, and we'll just have a little evaluation here again. So we're going to go to the correct bit and put a 1 there. And then if the val also has a 1, then this will evaluate to a 1 and write the 1 that it has. And if val has a 0, then it will evaluate to a 0 and write a 0. So that should work. Now, once we have pushed the data onto the data bus, now we need to tell the RAM to take it in. To do that, we need to turn on the chip. What I'll probably do is put it up here as a first thing. So we're going to do digital write. We're going to pull it low to turn on the chip. And I'm just thinking maybe we can give it this time here to fully turn on. I don't know how long it takes. It's probably much faster than our chip itself. And then down here, we'll actually enable the writing to go on. So we're going to pull this low too. And then maybe we'll give it 1 millisecond, an eternity to machines like this. Then we will put it back high to stop the writing, or not to stop it, but to just basically put it back into its idle state. And then we're also going to turn off the chip or deactivate it. So put this back to high. At least that's according to their instructions. Is that it? I think that's it, right? So we enumerate through every pin. We turn them onto the right mode, which is output. We set the value to each pin, and then we enable the writing to go on, and they're connected, of course, through the wires. I think that's it. Now, maybe we want to output something to ourselves. I guess I should do it. up at the top. We'll already have our X there. So let's do serial dot print X, and we'll make it hex. It'll just be a 1 or a 0, and then down here, after we're done looping, we can print our line. All right, so let us see if we can write some data. Now we can't verify it now, but let's just see if it works. So let's just put in a random address here, and let's put in a random value. Just do like 21. There must be some errors here. I've seen a T right here, UNT, yeah. All right, that seems to work. So again, we don't really have a way to test it right now, but we can see this number coming through, which is really what I wanted to make sure was going on. So we have our loop going through, and this should be backwards. I should have used a better number, but we could see 1 here. If we count backwards, 0, 0, 0, 1, then 0, 0, 1, 0 is 2, 0, 0, 1, 1 is 3, and 0, 1, 0, 0 is 4. And the reason why it's backwards, by the way, is I figure that the shift register is going to have it in reverse. The way I configure the shift register with the RAM is the least significant bit on the RAM input for the address is tied to the last bit in the shift register. So I'm hoping that if we push it this way, then it should all line up by the time it reaches the RAM module. What we need to do now is get our reading going on. So we have our write operation. Now let's get our reading. So mem R, right, for read. And in this case, we're just going to have a uint16 for the address. And what we're going to do here is very similar. We're going to have to loop through and turn all of our pins to input. So data start plus I, and then we'll have input. That's pretty much it for there. Now what we have to do, we have to pulse the address, of course. So we shift the address, push it onto the shift register. So now we have all the pins ready for input. The address should be on the address bus. Now all we have to do is enable the chip again, which again, I'll do it up here just to give it some time to turn on. Digital write, chip select low. Then down here, after we've done our processing, and we can turn on the output. So output enable low. Low is on. And then we can delay again. I don't think we need that, but I'll start with that. Then digital write, we can turn this back to high, and digital write, we can deactivate the chip. So now what we have to do, we need to enumerate through the pins and gather our data and build it into our byte that we could then, I guess, display or use. So after we enable the chip, I'm going to have an empty buffer, and we'll initialize it to 0. So our buffer is going to be built by all of the data, all the bits that are coming, and we're going to combine them together. So what we need to do is loop again, and now buffer is going to use a bitwise OR operation, and we're going to get the digital read of the pin, so data start plus I, bit shifted by I, right? So we're going to get the pin's data. That's simple enough, right? Whatever pin we're on, whether it's 0 through 8 or 0 through 7. And then we're just going to shift them. We're just going to make our way through the byte from right to left, or I don't like saying that, from least significant bit to most significant bit, setting each bit one at a time based on whatever the value is on that pin that we have gotten from the RAM. Now, I put this in the wrong spot. It should be right here. So we should be in between. And in this case, I don't need to delay anymore since we're going to have this in between. So we're going to enable the RAM and then get the data, and I think that's it. What we could do now after this is let's write it to ourselves. So we'll do serial dot, and we'll do buffer, and we'll just send in hex, and let's just send a print line. Sure, we could put these two together, but I always forget what commands they have built into this thing. So I think that's it. Not sure what else we would need. Data received. And then so what we can do now is at the top, let us write to a couple addresses. Say mem write. We have 1, 2, 3, 4. Do 1, 2, 3, 5. Do like 30. And mem write 0x 1, 2, 3, 6, 40. Something like that. And what we could do is we could do mem read the same values. And let's try and see if this runs. I think I need to write some better messages to the serial so we'll know exactly what's going on, but we'll just start here and see what happens. That compiled. That's a good sign. And now we have some data coming in, which is very slow. Let me update that actually. We do like 50 or something, so 10 times faster. I'll let this run though, I guess. So what's happening now is we are writing the 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 6, and we should be reading any second now. So this should be a read going through right now. Let's see if it gives us a value. Data received 40, which is not a good sign because it should be 21 at address 1, 2, 3, 4. 40. Wow. So we have we have 2 repeats, all 40s. Now, my first question is it a coincidence, or if I change this, will that change? So let's put FF. Let's print some data here, mem write operation, and in reading, let's put something there too, mem read operation. What I'm looking for now is it all FFs? I'm hoping that the write operation is going through fine and we're able to read it, because that would be a great start. All right, so we have 3 write operations. Now we have read, and we are getting FFs. Okay, so we know that the bug maybe is somewhere to do with the pins that we're setting. Let's randomize the addresses a bit and just see what happens here. So let's just do like 0, 1, 20, and let me do 23. I just want unique numbers every time or something like that. So 0, 1, 2, 3, 4, 5. Although technically, if I want unique addresses, I forgot this is actually 2 bytes. So let's do 0, 1, 2, 3, 4, 5, 6, 7, and let's do 8, 9, and 8, 9 again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 9. All right, here's our data, 3 writes going in. Okay, so now we're getting our data. Perfect. We have our 21, our 30, and our FF from these addresses, and we're reading them. So what does that mean? Let's go back. Let's just undo and make sure it's not a coincidence. There's our 3 writes, and now we're reading, and it's FFs again. So I think it's, oh man, it might be wiring, dude. I might have connected the wrong output, but no, because that doesn't make sense, because it would be consistent. Even if it's wrong, it would be right. You know what I mean? Like even if you have the wrong directions to go to a new house, you're still following the same directions every time to get to that house, even if it's the wrong place. So I don't know what the issue is, but I don't think it's code, because we're able to make it work only by changing the address. Oh yeah, I am silly. I'll record the breadboard and you could see it right now. So let me set up the camera. If you look at the shift registers, I am not taking the output from shift register 1 to shift register 2. So in other words, shift register 2 has all zeros. So we're only dealing with a 7-bit address instead of 15. So all I have to do is pretty much connect it to the input of the next one. So I'm going to just recompile this and send it. That has to be it. I mean, that makes sense. That's why some addresses, it's almost like the second half didn't exist. And you see how it's all 12s, right? This is exactly what was happening. 34, 35, 36, we're not making it. So if we cover this up and we see only 12, that's the address that it was receiving. That's why the last time it checked it was FF. And now we have beautiful results here. So this last set right here, 21, 30, and FF is exactly what we sent. So this is working well. It's good enough for me, like for what I need to make it work with hardware, I think. Pretty straightforward, a really nice little chip. Maybe what I could do is build this out to take some commands from the serial where we can tell it what to do. We can make like a baby shell program or something like that. It would be kind of cool to make it work that way. All right, so let's get a really basic shell program going here where we can control what the RAM is doing from the command prompt pretty much. So what I'm going to do first is just in the loop, I'm going to check to see if we have data that can come in. So if there's data to read, if there's no data to read, then we just return. But if there is data to read, then we're just going to write that out and it should print it in ASCII code. So let's test and see what happens. So if we send hello world, then what comes in? So we have a bunch of numbers here. I guess I should print line so we can see it come in a row. Let's just put A, B, C, D, E. So we should see 97, 98, 99, 100, 101. And then we have our new line character here, 10. So what this tells us is we can use the new line character as our end of sequence. So what we want to do is we want to buffer all the data that comes in until we reach new line, and then we'll put our null terminator. Let's get started on that. I think what we'll do is have a maximum size, so like buffer size. And let's say the max amount of characters that we'll accept is maybe 128 or something like that. And then we also need to have the actual buffer. So that's going to be a character array. And let's just call it buff, and we'll make it buffer size. And we also need to do what? We need to have an index. So let's do a size t, and we'll do like buffer index. And it automatically initializes to 0 when it's global, but I'll put that anyway. So now we have our buffer and we have an index to keep track of where we are. This could also be with a pointer, but I'll keep it. I think indexes are a little easier to understand if you're new to C. We know that we're going to have data here. So pretty much, I guess we can get the data here so we can play with it before we apply it to our array. And what we want to do is if C is a new line character, right? That's the end of the sequence. Well, let me start this way. We know what we want to do is in our buffer, we want to add at the current location and increment the value of C. So when a character comes in, we add it to our buffer, but we need to make sure that it's not the new line character. So if C is a new line character, then what we want to do is instead of putting the new line into our array, we want to actually put the null terminator. So that's going to be buffer at our current index without incrementing is going to be the null terminator, just to mark the end of it. And then what we can do is for now, we can put complete data and we could do serial.println buff. That should print and then we'll do return. So let's see how that works. All right, let's clear here and let's put ABC and see what happens. So you see our data that came in, we reprinted it back to ourselves ABC. Before we had it as the ASCII codes, but now we've put them into an array so that we can actually spell out the word. But we need to do a bit more checks here because if our buffer is too high, we want to protect against buffer overflows. So we'll put or buffer index is greater than or equal to buffer size -1 because we need to keep that last character for the null terminator. So if it's new line or we're over the buffer, then we're going to end the input. Otherwise, we're going to just keep on adding the character. So I guess what I'll do is I'll put an else here. I think that also is a little bit easier to understand rather than returning. if we have a new line character or we're over the buffer size, then we're going to do this. And if it's not any of these two, then we can just keep on adding our characters. So let's see how this goes. All right, so let's put in some testing. All right, testing comes back. That's pretty good. And then we can imagine that if we made the buffer really short, let's say we made it to 4 characters. Let's make sure that our buffer overflow is correctly cutting it off. Buffer overflow protection. So testing should cut out. And we have a problem here. So test. We're not resetting our buffer index. So let's do that. So let's do testing again. And we have tests and then we have in. So it ate the T. So really it shouldn't be an else. If we've reached the end of the buffer, then we want to send the data that they already sent, then reset it and continue saving, right? This is kind of a minor thing, but we're just going to continue to save the data. And to do that, we'll just explicitly check again, which is kind of messy. I think we can find a more efficient way to do this, but right now I'll just do that. So this way, it only stops taking input if it's actually a new line character. Otherwise, it will continue to save. And now we should get our missing T back. Let's put testing. And here we have TES, TIN, and then G is final. So this works well. We're limiting our buffer input. And there's a hidden null terminator. That's why it looks like there's 3. It's actually 4 characters coming out, but one of them is non-printable, as they call it. So let's put our buffer size back to 128 now that we know that we're running pretty well. And we can do a long test, and there we are. And if we put blank also works fine, nothing's wrong. And let's see if it messes up anything in the future now. So the next step, now that we have input that's able to get to our microcontroller, now we can parse it to look for commands. So the way I'm going to parse it is pretty simple. Let's just put a new function here called parse. Parse is going to take in buffer. We already have access to it because it's global. So let's imagine that we have a command. Let's say save 55 and let's say value 23. So this might be a command, right? And let's say that we have a very messy input, right? Spaces are sometimes a nightmare if you don't deal with them. So I'm going to deal with the blank spaces. So if we get a command like this, what we want to do is skip the white spaces until we reach a character, right? By the way, this is going to happen after we put our null terminator in, right? So that we can use this as a dependable reference for the end of the string. So what we want to do is we want to turn this into an array of tokens. So we're going to have save, then we're going to have argument 1 without the spaces, and then we're going to have argument 2. So at the top here, what I'll do is make an array of character pointers called argv. And let's make a size here. So we'll do define, let's say max args, and let's say 8. Oh, we shouldn't need more than that. So what we want to do here is let's create a pointer to take the location of the start of the buffered input. And what we want to do is while input is not the null terminator, right? So you could write this out, right? Once it's not equal to 0, of course, or you could check to make sure it's anything not 0, which is what's happening here inherently. What we want to do first is skip any white space that goes towards save. So while is space input, then we just increment, right? So while we have white space, we keep incrementing, bloop, 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 and then we reach the S. So if this was our input, we'd be at the letter S right now. So what we want to do is mark the location of the start of the first argument. So we're going to use, I guess I need argc here. So size t argc equals 0. So argc is going to keep track of our number of arguments, and then we're going to increment it for the next one. So this is going to be the location of input. So input increments, right? And then we reach the S, we mark the S inside our array, the location of it. So this might be like index, whatever, 4 or whatever. And then what we want to do is get the rest of the word, right? So in this case, now we're going to move forward. So while input, meaning while it's not the null terminator, right? It's an active character and it's not a space. So we're trying to get anything non-space. So the A, the V, and the E, and we'll put input here. Then we're just going to move it forward, right? So once it's not the end of the string and it's not a space, we're going to move forward now. So we're going to highlight save, right? And then it's going to move forward and it's going to see that the next character is a space with this function. So once we get out of this while loop, we're going to be at the first space after save. So we've successfully collected our word. So now what we want to do is actually mark the end of the word with a null terminator. So we're going to do what here? Well, we need to check if it's the actual end of the sequence itself, then there's already a null terminator there and we can just get out of this while loop, right? So for example, let's imagine that it was just like this. So when we get to the secret null terminator that's after the E, this is going to fail. And then we're going to check, is it a null terminator? Yes. And then we skip the while loop. But in the case of before, when we have other stuff here, then we're going to get to the space. And so we're going to get past this if statement. And what we're going to do is we're going to mark that location. We should also increment, I think, right? Yeah. We're going to mark this location as a null terminator itself. So what we're doing is we're splitting up these words and we're giving them, instead of the spaces after, since we're trying to put them into an array very cleanly, he's going to get his own null terminator here. And this guy's going to get his own null terminator. And this guy's going to get his own null terminator. And you might be wondering, well, how do we get to 12 if we have to pass through save? But that's because we're not actually going through save later on. These guys are going to be saved to their own positions with character pointers. So let's put some debug messages here. Parsing complete, arg I is less than arg C. Print out our arg of I to call parse here. Hello world. All right, so we have our parsing complete and we have args in it. You can see it split up here, hello and then world. So we have the args being split up. And now what we have to do is create our different functions. So let's do void save. Save is going to get his own arg count, and he's also going to get his own args. And load, same thing. When we finish parsing, we're going to figure out what command was entered and send it the relevant data. So let's do if argc is 1, then we know that we shouldn't have anything with 1. So we'll do not enough args. So let's make sure that works. Let's imagine that we put save without any data. It should say error, not enough args. What if we save 24? Then we at least have one argument and he likes that. Cool. So now what we want to do is compare the commands, right? We want to see, is save being entered? And really, I should modify this to be a bit better because it could be 0. So we compare strings, the first command and save. Then we know it's going to be a save command. So we're going to call save. What we're going to do is before save is argument 0, we could say, and the address is argument 1. So what we want to do is make the address argument 1. We don't want save to have to skip past his own kind of like call, so to speak. So we're going to reduce argc by 1 and also advance the array so that the first argument he gets is his actual argument. And then else we want to do the same thing for load, same thing. And then if none of those match, then unsupported command. Save called, load called. Save 25. So we have load called. I did something wrong there. Oops. This should be equal to 0. So we were actually checking if they didn't match. So we'll put save 15. So save called. What we can do now is check the argument. So if args, he wants at least 2 args, right? Not enough args. Load is going to do the same thing, but load only needs 1 argument. So if argc is less than 1, not enough args. So we'll do like save 15. So we should need 1 more argument. It should say not enough args for save. Print line saving and loading. I also need to get rid of a bunch of like the parsing. We know the parsing works now, so let's get rid of this. I'll put args here just so we still have the args. All right, let's see how this looks. So save 1523 again. Here's our args, save 1523, and then saving is a function that's going on. So let's get rid of the complete message because we know that that works. And now to save, what we want to do is we're going to expect hexadecimal values, right? Just to make it easy. So we can add on to this in the future, but for now, let's just do like this. So what we want to do is take the first argument and the second argument and convert them to hex and then use our actual functions that we already had. Call memory write, and we're going to cast it as a 16-bit integer. The result of string to long, which is the one that has a built-in hex. We can make our own hex converter too if you want to see that. We could write it arg v0, right? The first argument that save will receive. And at the end pointer, we could just put null. And then 16 is the number for hex, so base 16. So we're going to write to this address. And then the second argument is going to be cast as a 8-bit integer. And it's going to be the data. And we're going to put string to long, and we're going to do the second argument, null 16. And we can dress this up later. If you wanted to make it more readable, we could put address equals, and then we can replace this with address to make it a little bit more coherent. Long data equals, and again, we know that these arguments exist because we checked to make sure that we had them. The only thing is if we put a non-hex value, then we need to do some checks for that. But for now, we'll just get this working. So this should write to our memory location. And then on the load, we could do the same thing. 0. Oh, wait, I didn't put the details here. So we'll put null 16. This guy is going to just call memory read, and it's going to be uint as a 16-bit value, and it should output the data. So we have our initialization. Save to 1, 2, 3, 4, the value of 15. So we have a problem here. Memory write operation. Save 1, 2, 3, 4, 15. Those are our... Oh, I see my problem. I'm using argv, and it's actually args that's being passed here. Okay, so let's try this again. So we have written, hopefully, to location 1, 2, 3, 4, the value of 15, and let's try and load it. So load, data received, it says 15. Now, what I want to do is, maybe it's still buffered on our actual pin. So let's save to location 1, and let's do 99. Then let's save to location 2, and let's do 98. And let's save to location 3, and let's put 3, I guess. And now let's load 1 and see if we get that. So we should get 99, and we do. And let's do load 2, and we should get 98, and we do. Just to make sure we don't have buffering problems. And load 3, and we should get the value 3. So this works pretty simply. I can get rid of all of this stuff, which is some of our debugs from our memory read. We could just block this out for now. So shift, we have 2 of them. Comment this out, get rid of the semicolon. I guess we can comment 2. Save to 15, let's say value 23, and then load from 15. We should get data read 23. So you could see how we could build this out to do a lot more interesting things. Like for example, maybe we could save to 1 and we can put hello there. And what we can do is start at 1 for the H and then 2 for the E and 3 and have our system automatically save strings. The program itself, all these digital write calls, we can really limit them by using the registers directly. But again, this is just a test. But if you want to see that, let me know. We could also add like flags and stuff, load maybe to represent it as a string or as a character or cast as an integer. You can do all sorts of interesting things. Let me know if you want me to modify the code in any way or add more functionality. I'm very, very happy to do that. It's be a fun little project if we continue to add functionality. This definitely covers what I need. I just needed to make sure how it works for when I'm dealing with hardware, because with code, it's easy to change stuff up and test it. But with hardware, we're obviously going to have to change logic gates and stuff for any kind of test. So I'll try and add this chip to the 16-bit computer. I don't know what I'm going to do yet to make it work because something has to load the RAM. But for now, I just know that the chip works and it's very doable. Anyway, thanks again for hanging out, and we'll see what comes next.